Have you ever wondered why a circle continues to look the same as you walk around it? Or why a crystal appears perfect from every angle when you turn it in your hand? This might bore you. You might think, of course it looks that way. But today I'm going to tell you this. This simple observation harbors the deepest secret of the universe. And the person who solved this secret was Emmy Noether, perhaps history's least known but most revolutionary mathematician. Her discovery created such fundamental change that even Einstein called her the most important woman in the history of mathematics. So what did Noether discover? And why does this discovery form the foundation of every technology you use today, even your very existence? In 1915, the mathematical world was experiencing a revolution. Einstein's general relativity theory had shown that space and time were flexible fabric, that mass bent this fabric. But there was a problem with this new theory. The law of energy conservation seemed to be in danger. Scientists were scratching their heads. How could one of the universe's most fundamental laws lose its validity in this new theory? It was precisely at this critical moment that Emmy Noether entered the scene. And what she didn't just save the law of energy conservation, she revealed such a profound truth about the workings of the universe that this truth still mesmerizes physicists today. Noether's discovery was this. Every symmetry in nature necessarily corresponds to a conservation law. What does this mean? Let me give an example. Think that moving in any direction in space doesn't change the result. That is, every direction in space is equivalent. This is what we call translational symmetry. Noether's theorem says if every direction in space is equivalent, then momentum must be conserved. In other words, the total amount of motion of an object doesn't change. The equivalence of every moment in time also guarantees energy conservation. Rotational symmetry ensures angular momentum conservation. This isn't just a mathematical subtlety. This is the universe's most fundamental operating principle. To understand how revolutionary this discovery was, think of the scientific world of that era. Physicists were discovering natural laws by experiencing them, observing them. Newton's laws, Maxwell's electromagnetism equations all had emerged from observing nature. But Noether, by building a bridge between mathematical symmetry and conservation laws, showed that we could derive physical realities from pure thought. This implied that the universe itself was a mathematical structure. And indeed, thanks to Noether's theorem, we became able to predict which quantities would be conserved by looking at a system's symmetry. So what do these conservation laws mean in daily life? When we say energy conservation, we mean that the total amount of energy in the universe never changes. Energy can transform from one form to another, from kinetic energy to potential energy, from light energy to heat energy, but the total always stays the same. It's as if the universe operates like a giant accounting system where no energy is lost or created. Momentum conservation similarly means that the total amount of motion within a system remains constant. When a rocket launches into space, it propels itself forward by throwing fuel backward. The total momentum remains zero. But the real power of Noether's theorem emerges in its role in new physics discoveries. For example, in particle physics, when scientists discover new particles, the first thing they do is investigate what symmetries these particles possess, because symmetry determines what interactions are possible, what reactions can occur. The theory we call the Standard Model, which explains all known particles and forces, is fundamentally built on symmetry groups. Each particle behaves according to certain symmetries, and the conservation of these symmetries determine how particles interact with each other. The situation is similar in quantum mechanics. Why are atoms stable? Why don't electrons crash into the nucleus? The answer lies hidden in the symmetries of quantum mechanics. Electrons' wave functions reflect the atom's spherical symmetry, and this symmetry preserves certain energy levels. These conserved energy levels determine atoms' chemical properties and thus shape all chemistry, all life. So when you breathe, when your heart beats, when you think, even when you read these words, the conservation laws guaranteed by Noether's theorem come into play. Now let's go deeper and examine the concept of symmetry in different dimensions. In crystals, symmetry determines that crystal's physical properties. A diamond's hardness is related to the symmetric arrangement of carbon atoms. Graphene's incredible electrical conductivity stems from the symmetric properties of its hexagonal lattice structure. Even DNA's double helix structure is a result of the symmetric properties of chemical bonds. Nature seems to use symmetry as the foundation of beauty and functionality. But perhaps the most fascinating example is the symmetry of the universe itself. The cosmological principle states the universe is homogeneous and isotropic on large scales. That is, every place and every direction is fundamentally the same. This symmetry forms the basis of the Friedmann equations that govern the universe's expansion. Big Bang theory is explained by symmetry breakings in the early universe. The initially perfectly symmetric universe broke its symmetries with the cooling process, and these symmetry breakings led to the formation of galaxies, stars, planets, even us. Einstein's E equals mc squared formula is actually a consequence of Noether's theorem. The Lorentz symmetry of special relativity theory guarantees this famous relationship between energy and momentum. The equivalence between mass and energy emerges from the symmetric structure of space-time. This isn't just a theoretical formula. Countless technologies in our lives depend on this equivalence, from the sun's light to nuclear power plants, from PET scans to GPS systems. Symmetry breaking is equally important. The source of diversity in the universe is the breaking of perfect symmetries. The Higgs mechanism is an example of spontaneous breaking of the electroweak symmetry, and this mechanism is the process that gives particles their masses. If this symmetry breaking had not occurred, all particles would be massless, and the universe would be a very different place, probably one where life could not exist. One of modern physics's greatest mysteries is matter-antimatter asymmetry. In the early universe, matter and antimatter should have been produced in equal amounts, but the universe we observe today consists almost entirely of matter. This asymmetry stems from a small but critical breaking of a symmetry called CP symmetry. Without this symmetry breaking, matter and antimatter would have annihilated each other, and the universe would consist only of photons. Our existence owes itself to this small symmetry breaking. Noether's theorem plays a fundamental role not just in classical physics, but also in quantum field theory. All modern theories like quantum electrodynamics and quantum chromodynamics are built on symmetry principles. Gauge symmetry defines the electromagnetic force. Color symmetry explains the strong nuclear force. These symmetries determine how particles interact, which reactions are possible, how the universe's fundamental building blocks behave. Even in mathematics' most abstract areas, symmetry plays a central role. Group theory is the mathematical framework that classifies all types of symmetries. Lie groups describe continuous symmetries, and these groups have widespread applications in both mathematics and physics. Galois theory examines the symmetries of polynomial roots, and this theory determines which equations are solvable. Topology investigates shapes' invariant properties, symmetric properties. In artificial intelligence and machine learning, the concept of symmetry is also creating a revolution. Convolutional neural networks extract features using translational symmetry in images. Transformer models achieve success in language processing by distributing attention symmetrically. GANs, are generative adversarial networks, generate new content by learning symmetric properties of data distributions. These technologies are modern extensions of the symmetry conservation principles Noether discovered. Biology is also full of symmetry. The virus's icosahedral symmetry, DNA's double helix symmetry, topological symmetries, and protein folding all govern life's fundamental processes. In evolutionary biology, symmetrical structures often provide fitness advantages. Flowers' radial symmetry attract pollinators. Animals' bilateral symmetry is the optimal shape for movement. Human body symmetry is perceived as an indicator of health. So, what's expected in the future? String theory proposes that the universe consists of symmetric vibrating strings at the smallest scale. If this theory is real, all particles and forces will be different vibration modes of a single supersymmetric structure. Quantum computers are beginning to solve problems that classical computers cannot by using the symmetric properties of quantum superposition. Topological quantum computation aims to perform error-tolerant computation using symmetric knot structures. In cosmology, the nature of dark matter and dark energy is also being explained through symmetry concepts. If supersymmetry is real, every known particle should have a supersymmetrical partner, and these partners could be dark matter candidates. Periodic universe models try to explain the Big Bang using the universe's cyclical symmetry. Emmy Noether's legacy lives not just in theoretical physics, but in every area of technology. GPS systems use symmetry corrections arising from relativity. MRI devices convert spin symmetries into imaging. Lasers use coherent emission of electromagnetic symmetries. Fiber optic cables use symmetric solutions of Maxwell's equations for transmission. Solar panels benefit from the symmetric properties of the photovoltaic effect. Even in art and music, symmetry plays a fundamental role. Bach's fugues are full of mathematical symmetries. Geometric patterns in Islamic art visualize complex symmetry groups. Crystal structure symmetry affects gem cutting. In architecture, symmetry provides both aesthetic appeal and structural durability. In photography, composition rules use the psychological effects of visual symmetry. Philosophically, symmetry and conservation laws also contribute to debates between determinism and free will. If every aspect of the universe is subject to conservation laws, is the future completely determined? Or does quantum mechanics' probabilistic nature provide real randomness and free choice? These questions are debated across a wide spectrum, from physics to philosophy, from philosophy of science to ethical theories. In conclusion, Emmy Noether's discovery isn't limited to just mathematics or physics. It's the key that enables us to understand the universe's deepest order. Symmetry and conservation laws lie at the foundation of everything from atoms to galaxies, from DNA to artificial intelligence, from musical harmonies to cosmic order. These laws show that the universe isn't just chaos, but carries deep mathematical beauty and order. And perhaps most surprisingly, this order is comprehensible enough for the human mind to discover. This implies the existence of a mysterious and deep connection between the universe and human consciousness, as if the universe were designed for us to understand it. Emmy Noether's legacy continues to be the key that opens the doors of this understanding, and every new symmetry discovered in the future will illuminate even deeper layers of the universe. In conclusion, Emmy Noether's discovery isn't limited to just mathematics or physics. It's the key that enables us to understand the universe's deepest order. Symmetry and conservation laws lie at the foundation of everything from atoms to galaxies, from DNA to artificial intelligence, from musical harmonies to cosmic order. These laws show that the universe isn't just chaos, but carries deep mathematical beauty and order. And perhaps most surprisingly, this order is comprehensible enough for the human mind to discover. This implies the existence of a mysterious and deep connection between the universe and human consciousness, as if the universe were designed for us to understand it. Emmy Noether's legacy continues to be the key that opens the doors of this understanding, and every new symmetry discovered in the future will illuminate even deeper layers of the universe. But here's what truly makes Noether's discovery revolutionary. It predicted things that hadn't been discovered yet. Just like Maxwell's equations predicted radio waves decades before Marconi built the first radio, Noether's theorem predicted conservation laws in realms of physics that didn't even exist in 1915. When quantum mechanics emerged in the 1920s, physicists found that Noether's symmetry principles were already there, waiting to explain the new quantum world. When particle accelerators revealed exotic particles in the 1960s, their behavior was already governed by the symmetries Noether had mathematically proven decades earlier. This is the hallmark of truly profound mathematics. It doesn't just explain what we already know, it reveals what we haven't yet discovered. String theory, which attempts to unify all forces of nature, is built entirely on supersymmetry principles that extend Noether's original insights. If string theory is correct, every particle in the universe has a shadow partner, a supersymmetrical twin that maintains the cosmic balance. These shadow particles might explain dark matter, the mysterious substance that makes up 85% of all matter but has never been directly observed. The implications extend beyond physics into the realm of consciousness itself. Some scientists propose that the brain's information processing follows conservation principles similar to those Noether discovered. Neural networks maintain certain symmetries as they learn, and these symmetries might be what allows intelligence to recognize patterns across vastly different contexts. Or when you recognize your friend's face from any angle, or understand a sentence irrespective of the speaker's accent, you're using the same symmetry principles that govern galaxies and atoms. The philosophical questions become even more profound when we consider artificial intelligence. Machine learning algorithms discover patterns by finding symmetries in data, the same fundamental principle Noether identified in physical laws. Large language models like the ones powering modern AI find symmetrical patterns in human language that remain consistent across different contexts, cultures, and time periods. These AI systems are, in essence, automated symmetry detectors, finding the Noether-like conservation laws hidden within human communication and knowledge. Looking toward the future, we're on the brink of discoveries that would astonish even Noether herself. Quantum computers exploit the symmetries of quantum superposition to perform calculations impossible for classical computers. These machines don't just use symmetry, they literally exist in multiple symmetric states simultaneously until measurement collapses them into a single answer. Topological quantum computers, still in development, will use knot-like symmetries that are so robust they're virtually immune to errors, a practical application of mathematical beauty that could revolutionize computation. The search for a theory of everything, a single mathematical framework that explains all forces and particles, is fundamentally a search for the ultimate symmetry. If such a theory exists, it will be the most beautiful mathematical structure ever discovered, encompassing all of Noether's insights within a single elegant framework. This theory might reveal that space and time themselves are emergent properties of deeper symmetries, that the universe we experience is just the shadow of a higher dimensional symmetrical reality. But perhaps the most mind-bending possibility is this. If consciousness itself follows conservation laws, if human thoughts and decisions are governed by the same symmetry principles that control stars and atoms, then Emmy Noether's century-old discovery might ultimately explain not just how the universe works, but why we're here to understand it. The fact that mathematical beauty exists, that humans can discover it, and that it perfectly describes physical reality might not be a coincidence. It might be the deepest symmetry of all, the symmetry between mind and cosmos, between the observer and the observed, between the mathematician and the mathematical universe she inhabits. Every time you see a snowflake's perfect hexagonal symmetry, Every time your phone's GPS calculates your position using relativistic corrections, every time a flower grows in a Fibonacci spiral, you're witnessing Emmy Noether's legacy in action. The universe speaks in the language of symmetry, and thanks to one brilliant mathematician who dared to listen, we're finally learning to understand what it's been trying to tell us all along. The circle you walk around, the crystal you hold in your hand, the very atoms that make up your body are all part of one magnificent, symmetrical, and conserved and beautiful cosmic symphony. And you, as a conscious observer capable of recognizing this beauty, might be the universe's way of understanding itself. That's the ultimate secret hidden in the simple observation of symmetry. We're not just studying the universe, we're the universe studying itself, using the mathematical tools that Emmy Noether gave us to decode its deepest mysteries. The story of symmetry and conservation is far from over. It's the story of existence itself, and we're all part of writing its next chapter.